And we were talking about, consider the theorem there exist irrational numbers a and b, such that a to the b is rational. This theorem can be proven via a constructive proof or via a non-constructive proof. Dov Jardin's non-constructive proof, also attributed to Peter Rogosinski and Roger Hindley, proceeds as follows. Recall that the square root of 2 is irrational, and 2 is rational. Consider the number q equals the square root of 2 to the square root of 2. Either it is rational or it is irrational. If q is rational, then the theorem is true, with a and b both being the square root of 2. If q is irrational, then the theorem is true, with a being the square root of 2 to the square root of 2, and b being the square root of 2, since parentheses the square root of 2 to the square root of 2, parentheses to the square root of 2 equals the square root of 2 to parentheses the square root of 2 minus the square root of 2, parentheses, equals the square root of 2 squared equals 2. This proof is non-constructive because it relies on the statement either q is rational or it is irrational, an instance of the law of excluded middle, which is not valid within a constructive proof. The non-constructive proof does not construct an example A and B. It merely gives a number of possibilities, in this case, 2 mutually exclusive possibilities, and shows that one of them, but does not show which one, must yield the desired example. It turns out that the square root of 2 to the square root of 2 is irrational because of the Gelfand-Schneider theorem, but this fact is irrelevant to the correctness of the non-constructive proof. A constructive proof of the theorem would give an actual example such as a equals the square root of 2, b equals log sub 2, 9, a to the b equals 3. The square root of 2 is irrational. The square root of 2 is irrational, and 3 is rational. Log sub 2, 9 is also irrational. If it were equal to m divided by n, then by the properties of logarithms, 9 to the nth would be equal to 2 to the capital M, but the former is odd and the latter is even. A more substantial example is the graph minor theorem. A consequence of this theorem is that a graph can be drawn on the torus if and only if none of its minors belong to a certain finite set of forbidden minors. However, the proof of the existence of this finite set is not constructive, and the forbidden minors are not actually specified. They are still unknown. But I make a prediction. They will become known through the work of the boy genius Jacob Barnett.